Okay, well, welcome to the lecture for numerical simulation in metal forming process. Today's lecture, I can say it's the final lecture on the theoretical side of the numerical simulation in metal forming. Of course, we have many things to talk about for today. I hope that we can cover all. And then next week, you will start to practice some simulation and compare the simulation with analytical approach and obtain some result for different kind of metal forming process. And for today, our focus is on flow stress and flow curves. I think you know what's the concept, because we talked about the concepts in fundamental of metal forming. But today we will more focus on the mathematical. First we will talk about the parameters, the factors which affects the flow stress, and then we will focus on the mathematical modeling of flow curves. And of course I will explain that why it's important for the simulation and why we should have such a modeling in for the material in our simulation. Okay, for the first step, I'll talk about the necessity of modeling of flow curves from the point of view of simulation. Okay. Here you can see an example, a rolling process with different rolling mills, with different rolling stages. And okay, of course, it starts with the furnace stage, or reheating, that we increase the temperature of the material. And during this stage, of course, from the metallurgical side of view, we have the dislocation of this solution of participants, because when you increase the temperature, the participants in the precipitates in the material in the alloy solves, and of course you will have some grain growth. Besides, these two metallurgical phenomena affects the influence on the flow stress and mechanical properties. This is what we have for this stage, for the furnace stage. And then when we go to roughing line or rough milling, rolling, on each stage you will have hardening, recrystallization, phase transformation, grain growth, and again precipitation or precipitation hardening. So we can look into all these phenomena as a package, which on the stage that you have the temperature is high enough and you're applying the deformation, these macroscopic phenomena can affect on the mechanical properties and flow stress. And then again, sometimes, not all the time, but sometimes you have a furnace in the middle, again to make the temperature homogeneous and to bring up the temperature. And again you have rolling for the finishing. The final stages usually are the cold rolling, as you know, and then finally you have the cooling stage, which in this stage again the temperature reduces, and of course you will see the phase transformation, precipitation, and tempering effects again. So what I want to say on this figure is that, okay, you can see this is an example of a metal forming process. Of course, in forging, in drawing, any other type of metal forming process, you will have such a very change of temperature, increase, decrease, reduction of temperature, again increase the temperature in furnace and reduction of temperature. And temperature is one of the important parameters affects the flow stress. We will talk about it later. Beside the temperature, you have a strain rate, which plays an important role on flow stress. In this figure, you can see each metal forming process has a special range of strain rate or deformation rate by itself. Okay. So this figure I had to translate it to English, but okay. However, for different process, you see that the special range of deformation rate is required for the rolling, for drawing, and any other process. I will fix this figure and I will reflect the translated labels in the PDF file again later. So I talked about two important parameters, which is the temperature and strain rate, two state variables. I can say in simulation we call them state variables, and we have another state variable which is the strain, which strain is the amount of deformation, strain rate is the deformation rate, and the temperature. So these three parameters are the main state variables or the main influencing parameters on the flow stress. Okay, so how we characterize the flow stress? If you remember from fundamental of metal forming course, this is familiar to you. This is the yield locus, which determine your material is in elastic area or it's in plastic area. It means that it's you have elastic deformation or the plastic deformation is started. So and you know that we have different kind of criteria like the Tresca and von Mises. We talked about it before. Any kind of criterion you're using when you are inside this hexagonal or inside the locus, then you are in elastic area, and outside the plastic deformation starts. So if we want to convert this type of graph to a strain curve or flow curve, so for example, if you perform your test in a uniaxial compression test, then exactly here, this point is the critical value, which will be reflected here on this curve. And of course, the size and the form, and especially the size of this locus will not be same all the time. For example, if you start the deformation without any period deformation, at the starting state, this is the form of the locus, but when you apply the deformation, because of work hardening, the flow stress increases and the size becomes bigger. And if you have recrystallization, or if you have any kind of recovery or any other phenomena, then the size of the locus will decrease again. So this is the way we reflect the flow stress in a mathematical way and in a chart, in a flow, in a diagram. So why we need this? Because, okay, if you remember, we had such a curve here, and we talked about it before. It's reflect the relation between the strain and stress. Okay, in elastic area it's linear, we talked about it before. So in finite element method we have such a equation, and stiffness matrix in elastic area, this stiffness matrix is obtained using the model of elasticity. And so what we should put here for the plastic deformation? So exactly what interconnect the force, applied force, and the deformation together is the flow stress curve. So what we need for connecting the deformation and strain, stress and strain together is the flow stress diagram, of course in plastic area. That's why we need the flow stress and flow stress modeling, because when you want to give the flow stress to computer, you should, as I said before, if you want to give anything to computer, you should you should state it in a mathematical language, in a mathematical way. So this is the necessity. Okay, before talking about the mathematical side and the mathematical way of the presentation of flow curves, let's talk about a little bit about the factors which affects the flow stress from the both side of, like the macro, which is the temperature, strain rate, and strain, state variables, and the micro. I can say not only the micro, but from pico to micrometer scale. So we can categorize the influencing factor on flow stress in two different categories. One of them are related to the material side, and the other are the processing side. For the processing side, okay, we talked about it. These are the state variables which are determined during the your process, deformation process. Temperature, degree of deformation, or the strain, or deformation rate, which is strain rate. On the other side, for the material factors, chemical composition, of course, is the most important factor. It's the flow stress will depends on the chemical composition. It's your alloy is this iron based, or it's aluminium based, or it's copper based. Of course, it matters for the flow curve and flow stress, and also the alloying elements. For example, in the steel, in the type of steel, you have which alloying elements you have. Each alloying elements has its own effects on the flow stress. Okay, and the next item is grain size. Of course, you know the grain size influence on the mechanical properties, and if by decreasing the grain size, the mechanical properties and in flow stress and other mechanical properties, stress and flow stress increases. And crystal structure is another parameter. Like is it FCC, BCC? What's the structure of the lattice of your material? And stacking fault energy is another one. We'll talk about it later because it's important when you want to determine that which phenomena is happening. Is it dynamic recrystallization, or is it recovery, or else? And of course, the phase fraction and phase structure is important, because each phase, for example, in a steel, you know that each phase has its own mechanical properties, and I can say flow stress, because what is important for us is flow stress, so it's better to focus on flow stress. Dislocation density in the I can say in the pico scale is very important. Again, okay, in detail we'll talk about how it affects on the flow behavior of material. And the last one is precipitation. Precipitation hardening is another famous mechanism for hardening or for increasing the flow stress, or on the other side, when the precipitate solves in the matrix, you will have a kind of softening. As an example here in this diagram, it's the engineering stress and engineering strain for copper, pure copper. So you can see that how by decreasing the grain size here 0.2 to 4.2, how by decreasing the grain size the flow stress increases, and on the other side the elongation of course decreases. So this is I can say that this is the common trend for the effect of grain size on flow stress for any other alloy, of course. And then in this figure you can see the effect of temperature and strain rate. Okay, you can clearly see that by increasing the temperature, the flow stress decreases. Okay, what we could expect. And of course, here is the strain rate is 0.1. The strain rate here is 10 per second. So if you compare two curves at the same temperature, then you can see that by increasing the strain rate, the flow curve is shift up compared to that of strain rate 0.1. So we talked about the micro and macro factors which affects the flow stress. Now we will go a little bit deeper inside and on what we said for the material side, for the material factors. Let's investigate the effect from a very small scale like the picometer scale to the micro scale, and check what's the dominant phenomena on each scale and how it affects on the flow stress, and how you can model it if you want to model it. Because later we will talk about the different approach of modeling. And one of the approach of modeling is just the physical based models, which you should formulate these equations for example, dislocation density and other parameters to obtain the flow stress. This is one approach. However, today we will not focus on this approach, but maybe later in the lecture on the crystal plasticity, Mr. Gaiyum will talk about it more. But okay, today we talk about the theoretical background of that only. On this scale, which is the 100 picometer, it's a very small scale. So we have a mechanism of deformation hardening. What goes on in deformation hardening? You know that okay, we need the dislocation movement for the deformation, of course. And if you have a high density of dislocation, and or we call it the jungle of dislocation, then this high density of dislocation can play a role of barrier for the movement of the dislocations. Okay, imagine that you're walking in a street alone. Okay, of course, you can walk much more faster compared to the situation that the street is crowded, it's crowded street. So then you cannot move that much fast, and you need more energy to move, maybe because you have to change your path and pass through the other people, So the example for the dislocation or jungle of dislocation, it's exactly same with the person who is walking in a street alone or in a crowded street. So this is the way that we have deformation hardening in material. And okay, if you want to formulate it in mathematical way, then it's proportional to the square root of dislocation here. It means that by increasing the dislocation density, this hardening effect will increase. And the other parameters like shear modulus and Berger's vector, these are defined. These are the material properties. For each, from material to material, these values, this constant changes. But this is the dislocation density. In a little bit bigger scale, here we have solid solution hardening. In solid solution hardening, okay, this you can see here the example. It's in the atom scale. So the atoms of the alloying elements or the second elements sits in the lattice of material, and these atoms play the role of barrier on the way of the dislocation. So these atoms, even in the form of solid solution, can bring up the mechanical properties, or can increase the mechanical properties, or like it's better to say flow stress by themselves. And okay, you can see here in the mathematical formulation, it's proportional to the concentration of these atoms. So it means that if you have much more solved atom in the lattice, then this mechanism will be stronger. In a bigger scale, then, or in a nano scale, I can say, then we have the precipitation hardening. In precipitation hardening, now the atoms can form a particle here. Okay, it's much more bigger than an atom, but again, this precipitation can play a role of increasing the flow stress. How they can work? Not only the fraction of the precipitation is important, but also the interface of the precipitation and the matrix is important. It means that, okay, if you have such a big precipitate, or if you break down this size of the precipitate to the smaller size and distribute it, okay, which one influences more on the flow stress? Of course, in the case that you break it down to small particles, small precipitates, it will influence more on the flow stress. So this mathematical equation tries to formulate the effects of not only the fraction but also the volume fraction, but also the diameter, the size of the precipitate here. So here you can see by decreasing the size of the precipitate, if the fraction is constant, then the precipitation hardening effect will be much more strong. One scale up, in the scale of grain refinement, you have the effect of grain boundaries on the flow stress. I think this is familiar to you because we have the Hall-Page equation, which is in Hall-Page equation it's stated that the flow stress or the hardness or the mechanical properties of the material is proportional to the inverse of the square root of the grain size. Okay, so it means that by decreasing the grain size, the effect of by decreasing the grain size, the flow stress will increases, or the mechanical property increases. And the bigger or the biggest scale is the micro scale here. The micro scale. In the micro scale, you have a second phase here, and this phase can play the role of barrier or obstacle in front of the dislocations, and it can increase the flow stress. So in this case, not only the fraction of the phase is important, but the difference between the yield stress of the matrix and this second phase is important. It means that if your second phase is very harder than the matrix, then this effect, this hardening effect, will be stronger because this value is increasing. And of course, if the fraction of the phase, second phase, increases, it means that the fraction of the hard phase is increasing. So of course, the flow stress or the mechanical properties of the material will increase. So we could make an abstract on the mechanism, hardening mechanism in material, in alloys, in this slide. And here you can see that each of these mechanism affects on the formability, of course. Okay, in the case that you have the solid solution is strengthening, then the effect on the formability is not too strong. In the case of dislocation, in the pico scale, the effect on the formability is very strong. It means that the hardening, which is resulted from the deformation hardening or dislocation density, decreases the formability so much. And if it's the result of grain refinement or precipitation, then the effect on the formability is medium. It means that it does not decrease the formability too much. So you know that we need the formability beside the high mechanical properties. So it seems that these two mechanisms are better compared to the dislocation and the solid solution strengthening. because you will have higher mechanical properties, and on the other side the formability will not decrease too much. Of course it decreases, but not too much. Okay, now here we study the effect of state variables in detail. Okay, what was the state variable? Temperature, strain rate, and strain. So we start with temperature, and let's see how it affects on the flow stress. Okay, I think you know that by increasing the temperature, the flow stress decreases. Okay, so this should be the trend, as you can see here. And of course, it's that this reduction is a kind of exponential reduction here. So if you want to formulate it, so this, okay, this is, we can formulate it in this way. The e to the power of m1, then like theta is temperature, and m1 is constant. We talk about it. It's these terms we obtain is for a Freiberger model, Freiberger flow stress model. So, and this m1 to m8 or 9 are the parameters which are required in this model. Later we will talk about them more. Okay, however, in the middle you can see a second peak here. Anybody knows why this peak appears here? Okay, no feedback. I hope that you can hear me. Yeah, okay. Somebody's are typing. It shows that you can hear me. And so this peak is the effect of phase transformation. Yeah, or I can say, yeah, it's because of the secondary phase or phase transformation here. So you know, sometimes during the when you are heating up, for example, steel, then at the temperature of 680 or 700 something, you have a phase transformation to austenite. So this is the effect of phase transformation here. If you exclude this effect, but then the general trend of the effect of temperature on the flow stress is decrease of flow stress by increasing the temperature. Okay, so and here we talk about the effect of degree of deformation or strain on flow stress. So we have two phenomena here. One is the word hardening or hardening, okay, which is normally you know that by increasing the strain, the flow stress increases. This is the hardening effect. So we can reflect it in this way, in a mathematical way, or the phi to the power of n, which is similar to the Holloman equation, because in Holloman equation you have k epsilon or k phi to the power of n. So this phi to the power of n, or in Freiberger model phi to the power of m2, reflects the effect of hardening here. And okay, how about the softening effect? You know that you may have the recovery. Okay, if you do not have the recovery and the dynamic crystallization, then the curve would be like this. So the flow stress increases, I can say, all the time till it becomes plateau at the end. But when you have the recovery, then it drops a little bit, and if you have the dynamic crystallization, it shows such a behavior here. So, and this the dynamic recrystallization and the response of material to the deformation, it's exactly related to the stacking fault energy here. So with a higher stacking fault energy material, you will see the dynamic crystallization in the case of low stacking fault energy material with the low stacking fault energy. Then this dynamic crystallization will be much more weaker compared to the high stacking fault energy material. So you can reflect this term in this way mathematically, and this comes from here. So this hardening and softening together can be reflected using these two terms. And on the rate of deformation, or the strain rate, okay, here you can see if by increasing the strain rate, the flow stress increases. Okay, and what's the effect of temperature at the same time? Okay, if you increase the temperature, this increasement of the flow stress resulted by the increasing the strain rate will be less if you increase the temperature. If you decrease the temperature, so by increasing the temperature, this will change more sharply. By decreasing the temperature, this value will not, it increases but not too much. And of course, maybe you know that you can combine these two temperature and strain rate together with in a parameter which is named Zener-Holman parameter. Then of course then you can discuss the effect of both using the Zener-Holman parameter. And we talked about it in fundamental of metal forming before. So for the effect of strain rate, we can formulate in this way because it's a kind of exponential changes here, and the constant is given m8 here. And in some cases, not in all cases, but sometimes in ferrite, in aluminum alloys, by increasing the temperature, by increasing the strain rate, the flow stress decreases. Okay, this is the example which is behaving just the behavior is not similar to what we had here, but we have a decrease. It's the result of ordering phenomena, and of course it happens in a special range of temperature, not in a wide range, special range of temperature. So if your material is experiencing such a big phenomena, ordering effects, then you should consider this in the formulation, and this M3 is appeared here because of that, and I think it should have a negative value because it should decrease the flow stress. So if you give a negative value here, then it can reflect this effect for the specified range of temperature. So this is reflecting both these two phenomena, and this is reflecting these two phenomena, and this is just for flow stress change by increasing the temperature. Okay, later you will see that we gather all these terms and state the flow stress in a mathematical equation. This is another example. This is another mathematical model for flow stress, and this one is using some process parameter. Like, okay, here in this equation, this is the sigma s, the steady state stress, the peak stress you have in the equation, the peak strain, of course, and the steady state strain, and of course the strain and the flow stress. This is the flow stress, and you have a peak, a critical value, which is here. It's defined as a peak value. So two different mathematical equation is given for the strain which are smaller than the peak, and for this equation, and for the strain which are bigger than the peak. Here the dynamic crystallization happening. So the researcher who has developed this equation tried to model this behavior using two different equations, as you can see here. This is not important, their approach is not important at this moment, but if you check these graphs here, you can see that all the constants they have used, like CH, CS, and the peak strain, peak stress, whatever they have used, they are function of temperature and strain rate, both strain rate and temperature. All constants are function of strain rate and temperature. So it shows that if you want to model the flow stress in a mathematical way, of course you should consider the state variables, and which the temperature and the strain rate are much influencing the state variables on the flow stress. Okay. If you want to investigate the effects in a process, for example, a rolling process, here you can see the effects of dynamic recrystallization here. After rolling, of course, at the high temperature, after rolling, you will have during the rolling, you will have some dynamic recrystallization, and after rolling, some static recrystallization between this rolling stages happen. So if you look into the rolling gap here, exactly here, then you can find that the value of strain is not a constant value, because when the material goes between the rollers, and when you proceed step by step, the applied strain increases and it becomes plateau at the end. And of course the strain rate is not constant. The strain rate increases at the beginning, and then this peak is the peak of deformation, and then the strain rate decreases. Same for the temperature. You do not have a same temperature gradient from the surface to the depth. Of course, on the surface, because the material is in contact with the rollers, the temperature is lower, but in the middle the temperature is higher. And when you go on in the second rolling mill, because the thickness of the material decreases, then this gradient will be much more stronger, especially for the temperature. However, you can see a sharper peak in strain rate also, but for temperature also you can see that it's sharper compared to the previous rolling stage. Okay, so in bigger scale, for example, rolling stage, you can understand what's the effect of strain rate and temperature, and how they change in the process, during the process, and of course how they will affect the flow stress. So the flow stress in the simulation or in the reality cannot be just a number. It cannot be just a number. It should be temperature dependent, strain rate dependent, strain dependent, at least if we look into the matter from the process point of view. And from the material side of view, material point of view, okay, then we should consider the dislocation, density, precipitation, hardening, and other phenomena we talked about it before. This slide talks about, okay, you know that when we want to obtain the flow stress, we use the uniaxial compression test, or usually we use the Glibel test, which is a complex of uniaxial compression tests at different temperature and strain rates. So by using those experiments, we can obtain the flow curves at different temperature and strain rates. But normally it's a continuous experiment. It means that we start the deformation and we apply the deformation continuously, and finally the experiment finishes without any stop. But if you quit the deformation, then you will see a reduction of flow stress here compared to the case that you apply the deformation continuously. So you will see a drop. I think this graph is more accurate and it's more reliable. If you compare, then you can see that if you stop the compression and again start the compression, how the flow behavior of material drops and then it starts again. And even if you compare the different strain rate here, you can see that in the case of higher strain rate, this drop is stronger, and the increase, okay, it drops much more and then increases again. It's compared to other strain rates is much more lower than the continuous curve. So in the case of in the case that you have a non-continuous deformation, then you should consider the effect of the stop and starting the process on the flow stress. Then. So okay, here the graphs are talking about the effect of dynamic recrystallization. We talked about it. And some important terminology are given here. For example, this is the critical strain for dynamic crystallization. Above this critical strain, dynamic recrystallization starts. Okay. Note that this is not located on the peak. It means that the dynamic recrystallization starts before the flow stress reaches to this peak value. This is the peak strain, and then strain 0.5 is the strain that material shows when 50% of the microstructure is recrystallized, and then you have the steady states and where the dynamic crystallization is finished. So the rate of this hardening rate or softening rate, at the beginning you have hardening and then you have softening. So this is the rate, the hardening and softening rate, which is reflected for each range, and you can see how the rate of hardening and softening changes in each stage. If we plot the fraction of recrystallization, fraction of dynamic recrystallization with respect to versus strain, then you obtain such a S-curve in this way that shows the kinetic of the recrystallization, dynamic recrystallization. So usually we model this equation, this curve, using the Avrami equation, and this wave, first wave, second wave, and third wave, it shows that in practice, of course, you do not have a single curve. It means that it's not like that the grains start the dynamic recrystallization and then here it's fully recrystallized at the x equal to 1. Here is fully recrystallized. It's not like that, but you have different wave of recrystallization. It means that it's possible that a grain is deformed and recrystallized and again deformed and recrystallized in a very short period of time during the deformation. So the first curve is for the first wave of recrystallization, and again the grain is deformed and again recrystallized, the second wave and third wave and maybe more. And okay, this graph is talking about the effect of strain and strain rate on the kinetic of the dynamic recrystallization. So by increasing the strain rate and strain, you can see that the dynamic recrystallization finishes earlier. Or if you consider a constant fraction of dynamic crystallization, 50% here, if you increase the temperature and strain rate, then you will reach to this point sooner for 50% of dynamic crystallization. And this curve, for example, against is about the effect of temperature and time on the dynamic crystallization. This curve is showing that at a very high temperature and very low temperature, the time which is required for the dynamic crystallization is longer. Okay, maybe it's better to plot this line here, then you can see here is the start and here is the end, so it takes much more time from here to here, and of course from this point to this point, but at the temperature in the middle, the required time is much more, less time is required here for the temperature in the middle. And well, okay, these three graphs is talking about the precipitation during the dynamic recrystallization. So it's this steady state is the effect of precipitation during the dynamic recrystallization, and then again dynamic recrystallization. So it's these two is reflecting the effect of precipitation at the same time when you have the dynamic crystallization and precipitation. And this graph is plotting the strain versus Zener-Holman parameter. I talked about it before, and it shows that, okay, for example, at a constant strain, for example here at a constant strain, by increasing the Zener-Holman parameters, the phenomena you have will change. Here you have a metadynamic recrystallization, and if you increase the Zener-Holman parameter more than metadynamic recrystallization and static recrystallization together, and in this area just static recrystallization. Okay, I think it's enough for the metallurgical and material side of the modeling. Let's start talking about the mathematical modeling, which is the goal of this lecture. So based on what I said, we may have different approaches for modeling the flow curve or flow behavior of material. The first approach is physically based models or physically based approach. In this case, calculated the value or the flow stress is calculated from physical consideration in the slow function. Okay, so in abstract, in these models are related to the microstructure and the material side and the physics of the material. So for example, if you want to if you model the flow behavior or flow stress using the density of dislocation, precipitation, hardening, and those phenomena we talked about it before, then your model will be in this category, the physical based. However, we have some empirical models, which semi-empirical models here. In semi-empirical models, we use the temperature, strain rate, and strain rate, the state variables, in order to obtain the flow stress and to model the flow stress. However, if you look into the model, it's a mathematical model, but it's not pure mathematical. If you look into the model, you can see some metallurgical effects. You can find out some metallurgical effects, some metallurgical aspect, and some metallurgical theory which are implemented in the model. The example is the Freiberger model. We talked about it. Okay, each term, for example, for dislocation density, for precipitation, hardening, and for other parameters, we have a equation, or we have a term, but each term has a physical meaning in the equation. And the last category is the empirical models. In the empirical models, it's just pure mathematics. So you cannot find any, or the purpose is not implementing some physical phenomena in the model, but it's just pure mathematics, and the accuracy is important, not the physical meaning of the model. For example, the good example of these empirical models are the neural network, which is like the new generation of the models. So in neural network, you repeat the experiments many times, and you save for example, flow stress for the material at different temperature and strain rate, different condition. You save that values, and you just use the recorded data in a logic way. But this logic is not behind this approach. There is no physical meaning. It's just an pure empirical method. So based on what we have defined here, for single stage forming and multi-stage forming, in both you can use the physically based models or semi-empirical or empirical models, based on the material you have, based on the data you have, and based on that what is important in your modeling. Okay, so from now on we focus on the semi-empirical models, I can say, because in the case of physical models, I think Mr. Gayoum will talk about it a little bit more later in a separate lecture. But the common methods and the common models are the semi-empirical models, and we can categorize the semi-empirical models in four major categories. The first category is the Arrhenius equation flow model family. This is if you state the strain rate as a function of temperature and strain in a Arrhenius function. Okay, this is the model given, and these are the parameters, the activation energy, temperature, and so on. The parameters are introduced here. Or you can rearrange this equation, because our purpose is flow stress. So then we can rearrange this equation in this form and obtain the flow stress. And of course, we can make it abstract by putting the Zener-Holman parameter here instead of strain rate and temperature together. So it's the disadvantage of this model is that in the original form of the Arrhenius equation, or this Arrhenius equation flow model family, we call it family because many other flow models, mathematical or semi-empirical models, are developed by different researchers. You can see some examples here in the table based on this equation. It means that the base equation is this, but they have improved some parameters, they have changed some parameters to improve the accuracy of the model and such a modification. But still, the models are categorized in this under this big family, the Arrhenius equation family. So, okay, I was telling that the weak point of this model is that the effect of strain is not reflected in the equation. You cannot see the strain epsilon here and even here. So some researchers tried to reflect the effect of strain by defining the parameters in the equation as a function of strain in this form. So some polygonal equations for the strain are given in this form, and these parameters are used in the equation. So now the equation is a function of strain also. So temperature, strain, and strain rate all are included, and this the value of n is changing between 4 to 14. Of course, by increasing this number, the accuracy of the model in somehow increases, but some instability in the model appears. Increasing the order of polygonality or polynomial causes some oscillatory features at the highest strain. At the highest strain, then, if you can see some oscillation in the obtained value from the model. Okay, so this is the first category and first family. The second family is the Ludwig flow family model. I think this is familiar for you because this is just the Holman equation, and this constant term for sigma 0 is added here as a material constant. So this is the hardening exponent, and this k is also constant here. And Johnson-Cook is a model which is developed based on this Ludwig model, but in Johnson-Cook, the model is typical representation of Ludwig family and employs the fewest number of material constants. So it's a kind of simplification is applied in Johnson-Cook model. Another model, Sutton and Lowe, presented a remarkable extended Ludwig model, and based on this traditional form of the equation, but they tried to the constant like m here and k here, it's similar to this k and n, but these are not constant value, but they are temperature dependent. And the n value also, the work hardening exponent, is a function of strain. Okay, a b c d, these parameters are given here, so as a function of temperature, strain rate, strain. So it means that they made the model the basic model is very simple, but by giving the parameters as a function of temperature, strain, and strain rate by themselves, they make the model more flexible. When the model is more flexible, then you can decrease the error between the experiment and the model. Later I will show it on a graph. We will talk about the accuracy. So, and these are some other models, some other researchers who have developed their model based on this Ludwig model. So we cannot say that they have developed a new model, but they have developed a modified Ludwig model. Next family is the Voce model, which is, I can say, is the most famous semi-empirical model. And in this Voce model, you can, beside the effect of strain rate, and temperature, you can see the effect of dynamic decrystallization, which is reflected directly into the equation. So we can have a flashback to the definition of semi-empirical models. The semi-empirical models are the mathematical equation. However, you can see some physical meaning in the equations. Okay, here, dynamic decrystallization or hardening, you can see, and you can interpret the equation that, okay, this is related to the hardening, this is related to the dynamic decrystallization. So, and then for the fraction of dynamic decrystallization by itself, Voce suggested this equation, which, okay, this equation controls the kinetic of the dynamic decrystallization when the epsilon is higher than epsilon peak. When the epsilon is higher than epsilon peak, for the epsilon less than epsilon peak, of course, we do not have a dynamic decrystallization. However, as I told, this epsilon peak should not be, the critical value is not the epsilon peak. It's some value before the epsilon peak, as I talked about it before. But when you want to model it in a mathematical way, if you give the peak value on the curve is a determined point. It's clear that peak is here. But in the case of critical value for dynamic decrystallization, then if you give another, if you use the correct value for that, then it has no mathematical meaning, because peak has a mathematical meaning, but it does not have. So that's why maybe they use just epsilon peak here. Okay, so, and other parameters again here are given as a function of Zener-Holman parameter, which means it's function of temperature and strain rate. So you can see that the model becomes complicated if you substitute these values for epsilon s, epsilon p here and here, then the fraction of dynamic crystallization here, it becomes a very big equation with different terms, so which is really flexible to model the flow behavior of material at high temperature especially. And again, some example of different researchers who has used the developed some empirical, semi-empirical models based on the Voce model. And the last category, I can say it's not a category, but we have some other models which are not categorized in those three main families. For example, we have a CM model. This CM model was developed when I was a PhD student. I mean, it was developed before in the group where I was studying PhD, and then we continue working on that. And The equation by itself is very simple. It's a simple equation which says that the flow stress is a function of a strain rate. Here is a strain rate, and simply you have two constants, C0 and M0, but because it's the model is developed for the purpose of finite element analysis, so the constant, the value for the constant are obtained using the interpolation, and not a simple and single interpolation, but with a bilinear interpolation. It means that the temperature is changing and strain rate is changing, so at step and point by point the software calculate the new value for the C0 and M0. So these two values are not, I can say they are not constant, and they are calculated for each node based on the temperature and the strain rate which is applied. Then this value are obtained, and the flow curve is also obtained. So if you can, of course, you can calibrate your model with few given temperature, but for the temperature in between and for the strain rate between the sample points you have for the experiment, then the software on the it calculates automatically the value for M0 and C0 using the bilinear interpolation and using this formulation. So this is the way it works. It's simple, but it's really effective and accurate in the case of modeling the flow stress. And the final model is the Freiberger model. Excuse me. Which is, of course, is important because it's developed in Freiberg, in Tübingen, and as I know, the idea started according to this Haduk and et al. Research in almost 100 years ago, I think, and the term and the meaning of the term, we talked about it in the slide. We were talking about the dislocation density, precipitation hardening, and the other parameters. You can see those factors are put together here, and then step by step during this 100 years ago up to now, the model is improved. Some terms are added, and some modification is applied on the model to make it more flexible and more accurate to model the flow behavior of materials. So as I know, it's I heard that more than 35,000 rolling experiment is carried out up to now to obtain these parameters and for different materials, and to make this model applicable for different kind of materials. And 35,000 rolling experiment, it's big amount of test. So it's a summary about the models. We talked about it. So you can see different models which can, of course, can be categorized under the main families of the flow model we introduced. And then here you can see the number of parameters in the model. Each model has what number of parameters, and why this number of parameters is important. Okay, today's with the computer we have, the number of parameters does not matter so much. Okay, if it's like the power law model with 2 parameters, or like the Johnson-Cook with 5 constant or parameter, or the modified Johnson-Cook with 6 constants, and the Hansel-Spiegel with a much more constant, 10 constant, 18 constant, Voce. The number of constant today's with the computer we have it's not important anymore, because we have a high capacity of calculation with the computers, so we can give the different we can give the high amount of information, high amount of many constant to the computer to receive a better result, of course. So from the calculation point of view, it's not that much important. Then the thing is important is that when the model becomes complicated, when the number of parameters increases, then you should have a way. You should have a way to obtain the parameters for the each material, and that's, of course, that is important. But if you have the parameters, then you can give it to the model, to the computer, and obtain a better result, a much more accurate result with higher number of variables in the model. Okay, so, and this is the interface. This is an example of the interface of a software. So when you want to give the material flow behavior of the material in software, so you can see here some of these models are available. So if you click on the appropriate model, then you should give the constant for the model, the value, and this is one way. Of course, in many software there is a database for the material which can load the properties and flow behavior of the material from the database. However, sometimes in your research your material is not in database, or the data recorded in database is not reliable for you, then you can use this kind of mathematical modeling for flow stress if you can carry out your own experiment and if you can obtain your result and calibrate the model, of course. Okay, on this slide it's about the accuracy of the model. So it's comparing the model with the experiment here, and this is the Hansel-Spittel model, and it shows that, okay, here Hansel-Spittel model is showing a big error between the experiment and the model, and for this temperature here it's a big error on the peak, okay, because in Hansel-Spittel I can say that it's just modeling the hardening in some way, not on this modeling of the softening is not strong. However, here then you can see the Voce model that we said that it's the softening and dynamic recrystallization is considered in the model. So the red line is the experiment, so it's a good match between the Voce model and the experiment, but this CFF model and PELF model are in the family of the CM model, as I said, that numerical models, and if you compare those, you can see that they are much more accurate compared to these other semi-empirical models. And the error is so small if you use the CM model, which uses the bilinear interpolation to obtain the parameters in the numerical simulation or in finite element analysis. So, and this table is talking about the effect of alloying elements on the flow stress in some models, not too many models, but some few models. Here here I can show you a model here. It's a model for the steel which reflect the effect of some alloying elements like the carbon and sometimes the silicium on the flow stress. Of course, the temperature and the strain rate are also in the model. The advantage of this kind of model is that they are including the effect of alloying elements, but their application will be restricted, of course. They are not the general models. This is another example of the model that's developed by Medina and Hernandez. This model is also, of course, the strain rate, temperature, strain are reflected. It's an Arrhenius model. You can put it under the Arrhenius family model, but some parameters like Zener-Horman parameters, some activation energy, and some parameters are given as a function of chemical composition, as you can see here. So this model can provide the flow stress for different alloying steel. But of course the range of the alloying steel is limited, and I don't know how is the accuracy of the model. Okay, and now we can summarize our lecture. So we talked about the different parameters affecting on the flow stress from the process point of view, which are temperature, strain rate, and strain, and from the material side of view, the dislocation, density, precipitation, and the other parameters. And then we talked about the effect of each parameters in detail, and then we introduced some semi-empirical models for mathematical modeling of flow stress. And the theoretical background for the finite element or numerical simulation in metal forming is almost covered here at this moment. So I will close this session here and I stop recording, but I have another topic which is not included in the PDF, and it will not be in the recorded in the lecture, which is about the introducing some software, the famous software in the field of metal forming, because next week we will start to work on the simulation, so it's better to have a overview. But because it's a little bit it's not academical, it's a little bit commercial, so it's not included in the lecture and also in the PDF. Okay, is there any question up to now?